All right, we're just moving on from part one now on the centripetal acceleration, centripetal force or circular motion lecture. So here we go. So here's another equation. If you manipulate the equation further, you can get centripetal acceleration is equal to 4 times pi squared times the radius divided by the period squared. This is another useful equation. And this page itself, this is quite important. I suggest you pause this and write down everything except the one that's already on your equation sheet, right? I haven't talked a lot about this year because most of the equations have been there, but I recommend you get, that AP equation sheet you have, I recommend you just write all over it, at least for the purposes of this class. Now, if you are taking the AP test, clearly you're going to need to have just a blank, you're just going to have a normal AP equation sheet for that. But for the purposes of this class, I am perfectly fine with you writing different equations on there. And I suggest you write these down. So we've got, so these are all useful equations, different ways of getting different things in terms of circular motion of objects. So pause it, write them down on your equation sheet, and we've probably already done that, so let's move on. All right, so if you have a car turning at all, basically, that turn can be thought of as a segment of a circle, and the static friction of the car, that's the friction, because the car, as the car is turning, the car wants to keep going in a straight line, and so there's friction that keeps the car from basically skidding out. If you ever hit a patch of ice while you're trying to turn, you know this all too well. And of course, that static friction, that is your centripetal force, right? And that is pointed towards the center of that that segment of circle that you're turning on. Okay, so I've got a 14 Newton car traveling at 25 meters per second around a curve. So this is essentially what I was just talking about, right? That's what that whole picture was before. You got a car. The force due to gravity on that car, remember, that's not weight, it's just, or that is weight, excuse me, the weight of the car. It's not giving you the mass. Be careful there, I could see that being a problem. And the car is traveling with a velocity of 25 meters per second. And so then the radius of this, it's turning, right? Well, that's not the best picture in the world, but the radius is 200 meters, right? And I need centripetal acceleration. Well, I have an equation for that, right? Centripetal acceleration equals velocity squared over the radius. And so that was right off that last couple slides ago where we had all of equations. This is just one of them. I have the velocity, so I got 25 meters per second. That's all squared. And then divided by 200 meters. Now when I plug that in my calculator, I end up getting like roughly 3.1 meters. So let's look at the units real quick. That's kind of interesting. So I got meters per second, but they're squared, right? Right here. So it's actually meters squared per second squared divided by meters. So when you divide by meters, then one of the meters in the meter squared gets canceled out, and then that gets canceled out. So you're left with 3.1 meters per second squared, which is a unit for acceleration, so we know we're good to go. All right, so now we got, this time I'm supposed to figure out the force that maintains centripetal acceleration. All right, that's interesting. So again, I got it's all the same, right? I have the radius, I have the, well, let's write out what I have. The radius equals 200 meters. The force due to gravity is 1,400 newtons. And And I got velocity, that's right, excuse me, 25 meters per second. So I am supposed to figure out the magnitude of the force at blah, blah, blah. Yeah, so the force, so that's that's basically the friction, right? Which is pointed towards the center of the circle, that's the centripetal force, right? There's always going to be some force that is, when something's in circular motion, there's always going to be some force that is keeping it from going in a straight line, right? In this case, it's friction. The wheels of the car are turning. The car wants to go straight. Like I said before, if you've ever accidentally hit a patch of ice while you're trying to turn, you know that without friction, you'll go straight. So friction pulls you towards the center of the circle, and so friction is centripetal force, right? So centripetal force, in this case, and of course we know centripetal force equals mass times velocity squared divided by the radius, right? So I could say, well, the force due to friction equals mass times velocity squared divided by the, that's the same thing. I'm saying the same thing, but I'd like to call it what it is. It's the force due to friction, but it's also the centripetal force, so I guess either way I'm calling it what it is, right? So in this case, let's see. I have the mass. Oh, you know what? Careful. I don't have the mass. I have the force due to gravity, and it's 14,000 newtons, right? So let's quickly look at how do you solve for that? So force due to gravity, right, equals mass times the acceleration due to gravity. So if I want the mass is going to equal the force due to gravity divided by the acceleration due to gravity. So what does that mean? That means mass equals 14,000 newtons divided by acceleration due to gravity, 9.8. I want to plug that in my calculator. I get roughly 1428, we'll say 0.6, and that's kilograms. Now, if you want to know how that worked out, well, that's because a newton, well, and this 9.8 is acceleration, right? So it's meters per second squared. So that ended up being a newton over a meters per second squared, which is a newton, remember, is a kilogram meter per second squared, right? And so when I divide kilogram meter per second squared by meters per second squared, I just get kilograms. So that's how that works out. A newton is a weird unit that's made up of a bunch of units. So either way, that's how that works. So now I've got my mass, right? So the mass is 1428.6-ish times the velocity squared. The velocity is 25. Oh, I should put kilograms here. 25 meters per second. And this is all squared. And then that's got to be divided by the radius. And the radius is what? 200. 200 meters, because it's a radius. And then when I pop that in my calculator, again, because a newton is a kilogram meter per second squared, and then this is squared, so I'm going to end up with a newtons again. So I end up getting 4,464.4 newtons. So and that's our force due to friction. And it seems like a lot, but it's a car. That's the force it keeps that's the force it takes to keep a car from sliding off the road. It's a good amount of force you're going to need. Okay. The last thing it says, I can't read it because of my little recording thing. Hold up. It says all the same exact things, but now I'm supposed to figure what's the minimum coefficient of static friction between the tires and the road that will allow the car to run the curve. Oof. Okay, for this one, I always remember the coefficient of friction equation. I remember because it's the fun equation. So I know the force due to friction equals mu times the force, normal force, like fun. That's like how I that's how I remember that. Don't worry about it. That's how I remember it. Okay. Very, 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 very interesting. Okay, so that is my so that means what is the coefficient of friction equal then? It's good if you're supposed to solve for the coefficient of friction, you should first do this, right? It equals the force due to friction divided by the normal force, right? Well, the normal force is given to me. It's right because that's the weight of the car, so that must be the weight. I mean, we could draw the free body diagram, but I think for the most part, if the car is on flat ground, it doesn't really take much thought to know that the car is not accelerating towards the center of the earth. The car is not accelerating towards the sky. That means the 14,000 newtons that's pushing down, that road must be pushing back up to keep that car where it is. So that means that the normal force is 14,000 newtons. And then what's the force due to friction? We just figured that out, guys, right? Force due to friction, we just figured out was 4.4 newtons. And probably should lose some sig figs, but I don't know. I'm not really thinking sig figs these days. Anyways, 14. So force due to friction, I just said was the 14,464.4 newtons, and then the normal force is the 14,000 newtons, and then you put that in your calculator, you get 0.32, and that's reasonable, right? Remember, with the normal force, with the coefficient of friction, as long as it's like less than 2, above 0, you're probably good. I mean, if you get like a 0.00 something, that's like really, really, really low friction, so that's probably not right either. But 0.32, sure, that sounds reasonable. You know, it's a coefficient. You know, you're probably going to get, it's a low number, and that seems good.